All right, so we've just handed back test number 1. The median on this test was an 81. What that means is that half the folks who took it scored higher than 81 and half scored lower than 81. Again, if you have individual questions about your test, just see me individually, like right after class today or any day. On the inside of that front page of the test, you'll see a current snapshot. That is to say, here's what your current homework grade is, your current quest average, and then the one test that you've taken. And if I smush them all together according to the percentages on the syllabus, here's what grade you would get if the course ended today. Okay, so brand new packet today. Today we cover something called the Pythagorean Theorem, and we begin our section of problems on exponents and radicals. Exponents and radicals covering the next 4 classes. Any questions on the calendar? Okay. So let's jump in here on the top of page 3. So pages 1 and 2 are a reference sheet that we'll be using today and in the next bunch of classes, but we're going to skip it for the moment and take a look at our daily summary. In this lesson, we solve word problems using the Pythagorean theorem, and we begin our exploration of exponents by using certain rules to simplify expressions containing exponents. Number 1. The Pythagorean theorem states that for every right triangle, the sum of the squares of the legs equals the square of the hypotenuse. So you've seen this theorem before. It's the most famous theorem in all of mathematics. You can see a right triangle there. 2 of the sides are called A and B. Those are the shorter sides, and those are called the legs of the right triangle. The longest side is labeled C. That's the hypotenuse of the right triangle. The important thing is when you use the equation A squared plus B squared equals C squared, you put that long side by itself in the equation. So let's see if we can solve a problem using that Pythagorean theorem. You are shopping for a home entertainment center and find one at a good price. The space for the TV in the entertainment center measures 17 inches by 21 inches. That's a rectangle. You are wondering if your 27-inch TV will fit in this space. Note that TVs are advertised by the length of the diagonal. So let's go ahead and draw a rectangle. This is going to be the space in the entertainment center. And we're given that the dimensions are 17 by 21. So 17 here, 21 here. And we're trying to figure out, we're on page 3, trying to figure out if our TV will fit. And it's called the 27-inch TV, but that 27 inches is the diagonal of the TV. And so it sure feels like I should draw the diagonal inside of my rectangle. So let's draw that diagonal right there. We are going to use this most famous theorem to find out how long the green thing is. And then we're going to compare that green length to the 27 inches that we're trying to squeeze into that space. So let's give it a shot. What's a good letter for green, A, B, or C? For sure, that is C. That is the hypotenuse, the one opposite the 90-degree angle. So let's use our theorem. I'll just write it again here. A squared plus B squared equals C squared. A and B are 17 and 21 in either order. I'll do 17 squared plus 21 squared. But it's okay if you reverse those two. Important one is the C. C has to be by itself in the equation. Okay, this is going to be a calculator active problem, but not just yet. Let's go ahead and now look at that first page handout that we skipped over. Rip it off of the packet. We are going to use it a bunch. You want it to be separated from the packet. On the front side of this thing is a big old table with lots of numbers in it. The first column is just counting, does it just say number in the first column? What does it say? Number. First one is just counting 1 through 30. The second column are the perfect squares. That's where we want to be. For example, 7 squared, you know it's 49, but just look and find that in the table. Go to 7 in the first column, and then go over to the next column, and you see the 49? Yes? Everybody with me? Yes. So go ahead and look up 17 squared, in case you don't happen to know that one by heart. What is it? 289. Plus, in the same table, find 21 squared. Go to the 21, over to the squared column, 441. Super. And that's equal to C squared. So we're going to use this table a bunch, and the reason that I don't want us to use a calculator here is that the very next quest, it's coming up in a little ways, is the only non-calculator quest of the entire semester. But you're going to have that piece of paper in your hands, and so you need to be able to read the squares off of that paper like we just did. Okay, so we'll add this up. Let's see, that's 0, carry the 1, 3, carry the 1, 730 is what I get. And this is a place where we are going to want the calculator, but what are we doing to both sides? What's the opposite of squaring a number? It's square rooting. So we're going to talk about square rooting in detail in a couple of classes, but I think it's something we've seen before in a previous class, so we're just going to use it. Square root of 730, that's the answer to our problem, and that's something you can use the calculator for. So if you happen to have a calculator, go ahead and grab it and give me the square root of 730. If you don't have one or you don't know how to do the square root on it, I'll help you during the activity time today. Who's got a number for us? Just one more. 27.01, typing that on the calculator. That is how long the space in our entertainment center is on the diagonal, 27.01 inches. We have a TV that is 27 inches. Will it fit? Just barely, right? 27 is just a hair under the 27.01. Did you see how exciting I made that, 27.01? Good. All right. So we're not going to talk about the Pythagorean theorem anymore. It's just a standalone topic, and we're about to do a topic that is going to carry with us for like the next few weeks. But the Pythagorean theorem will come up on the quest, and it will come up in the homework. And how do you know to use a Pythagorean theorem? You got a right triangle. Like it's as simple as that. Have a right triangle with the sides, 3 sides. You're using that theorem. Okay, but now we're going to shift gears and talk about exponents. Many of the rules for working with exponents follow naturally from the definition of an exponent. Here are some examples. So just a minute ago, we talked about 7 squared. How do we know it's 49? Because 7 squared means 7 times 7. 2 copies of the number 7. What does 5 to the 4th mean? It means a bunch of copies of 5. 4 copies of 5, all multiplied together. 5 times 5 times 5 times 5. That's 625. What is 2 to the 8th? It's 2 times 2 times 2 times 2, 8 of them all together. Right? Okay, so just some vocabulary. If you see x to the n, we call x the base. So 2 is the base up there, and n is the exponent. 8 is called the exponent. That's vocabulary. Okay, we've got 5 laws of exponents coming up right here in this table. And I don't want you to just, I mean, I guess at some point I want them to be memorized, but I really want you to understand why these things that we're about to talk about are true. Instead of just saying, oh, well, Ian says there's a fact, and so we just believe Ian, and then we'll just memorize this thing and use it. I want us to really understand why they're true. So let's take a look at this example right here. 3 to the 5th times 3 squared. We're going to see if there's a way to combine these two things. They both have a 3 in them. Maybe it's 9 to the something. Maybe it's 3 to the 10th. I don't know. There's a lot of things I can do with the 3 numbers up on the board to try to come up with some reasonable way to smush these things together. But let's just write them naively right now. 3 to the 5th is 5 copies of the number 3, and 3 squared is 2 copies of the number 3. And if I just gave you this thing and you ignore the parentheses because we don't really need them, how many copies of the number 3 do you have? 7, right? And so is there a shortcut that you can do with the original 5 and 2 to get the correct power of 7? You just add them together. Did the 3's multiply? No, all we were doing was counting 3's. It's not 9 to the 7th, it's 3 to the 7th. And so that property is listed out over here. X to a power times x to a different power is equal to the same x. You copy that x, and then you add the powers. Okay, moving on to the next example. We've got 3 to the 5th on top, and again, I will just write out over there, and then we've got 3 squared on the bottom, and we will write it out there. And then we can cancel, right? How many of those 3's go away? 2 of them, right? These 2 can cancel with these 2. And so how many 3's are left over? There are 3 of them left over. Is there some simple thing we can do with the 5 and the 2 to understand that there are going to be 3 left over without writing it out? What can we do? We can subtract them. And so 5 minus 2, 5 minus 2, that's it right there. And so that is written out right there. X to a power divided by x to a power, x to the m minus n, 5 minus 2. Okay, You could get away with just learning that form of this property, but I'm going to show you the reciprocal form, the flipped over form. Let's take a look at the same problem, but upside down. Now the 3 to the 5th is on the bottom, and the 3 to the 2nd is on the top. How many of those 3's cancel? 2. Is the answer, again, 3 to the 3rd power? No, it's 1 over 3 to the 3rd power. We canceled all of the 3's. We needed a placeholder. We didn't actually need it before, but we could have put a 1 when we got rid of all those 3's. We need it here. You got to make sure that you keep the 3 to the 3rd on the bottom, and so you have to introduce this 1 on the top. And so what's the shortcut? Well, I had a 5 and a 2, and what do you do with those powers to get the right final power? You subtract them, but because there are more 3's on the bottom, that's where the 3's end up at the end. That's what I know, is that when I cancel, the 3's are going to be left over wherever there were more of them. And so here's the same property, looking at it from the bottom, the perspective of the thing on the bottom, x to the n minus m, but you put it in the bottom. So wherever there's more, that's where they end up. Okay, next up, 3 to the 5th, the whole thing squared. So again, we're naively writing things. 3 to the 5th squared really means 3 to the 5th times 3 to the 5th. Yes? And then 3 to the 5th is really 5 3's written out. And then the other 3 to the 5th is another 5 3's written out. How many 3's are there altogether? 5 and 5, that's 10 3's, yes? What's the shortcut? Looking at the original powers to build the correct power of 10 is we multiply those powers, right? And so if you have x to a power, the whole thing raised to a power, you get to multiply those two powers together. This is the first sign of difficulty for students right here, is that up above, 3 to the 5th times 3 squared, you could very easily convince yourself to multiply those powers, and you could very easily convince yourself to add the powers when it looks like that. And those are reversed, and I don't want it to be like straight up memorized. If you don't know what's going on, if it's not comfortable, just write out this example. Put it on your reference sheet. Have it in front of you when you're doing the homework. Okay, last two kind of look similar. In the first one, we've got two things multiplied, all raised to a power. In the second one, we have two things divided, all raised to a power. But it's basically the same thing. It's just multiplication versus division. So let's take a look at an example. 3 times 4 to the 3rd. Sure, it's 12 to the 3rd, but that's not what I'm after in this case. 3 times 4 to the 3rd means give me 3 copies of 3 times 4. These parentheses are not necessary. It's just straight multiplication going all the way across. And we can multiply things in any order without changing the outcome. So I'm going to choose to group together the 3's. I'm going to put all of them in the front. 3 times 3 times 3. And then I'm going to put all of the 4's in the back. 4 times 4 times 4. How many 3's were there? 3. How many 4's were there? Also 3. So at the end of the day, 3 times 4 to the 3rd really becomes 3 to the 3rd times 4 to the 3rd. And so I think of this property as being the distributive property, like that exponent right there distributes into both the 3 and the 4. You see that? I'm going to use the word pseudo-distributive, and I had quotations around the word distributive, because distributive property is something like this. It is multiplication on the outside of addition or subtraction. That is the distributive property, nothing else. This reminds me of that, but it is not technically called the distributive property. The same thing works when you have division. 3 over 4 to the 3rd. If you write it all out, you will see that that power of 3 comes in and pseudo distributes to the top and the bottom. 3 to the 3rd over 4 to the 3rd. Okay? That's written over here with x's and y's. All right. So those are 5 laws or properties. We're actually going to skip this next page. That's going to take us a bunch of time. We're going to come back to it in a couple of minutes. But let's go over here to number 6. It says it's important that we can handle negatives and exponents together. So here's the first one, negative 4 squared. The second one sounds the same, negative 4 squared. And the last one is negative 4 squared. And there are lots of ways to get these things wrong, but we got to make sure we can get them right. The answer to every one of these questions is either 16 or negative 16. But whether you pick the right sign or not makes all the difference. So let's focus on that. -4 squared, what does it mean? It means -4 times -4. Which of my two answers is that? That's positive 16, no problem. The middle one, -4 squared. Some students read this thing as being the same. They're saying, okay, I see the number -4 and it is being squared. It is being multiplied by itself. That is not what this problem says, and this is not correct. This negative sign is really a -1 times. In fact, every negative sign you see, you could think of as just being -1 times the number. What is -8? It is -1 times 8. Yes? Every negative sign just means -1 times the number. So if I write this problem this way, you start to see that that square is actually pretty darn far away from that negative sign. And I've got multiplication and exponents, order of operations. Remember PEMDAS? What are we doing first, multiplication or exponent? We're doing the exponent first. That's the E from PEMDAS. Multiplication comes after all the exponents are done. So this is really -1 times, and how much is 4 squared? That's 16. And how much is -1 times 16? Is -16. And so the analogy I like to give for this one here, you guys have seen like either pictures or skeletons of Tyrannosaurus Rex. Massive dinosaur, but what can you say about the arms of the T-Rex? Really short arms, right? Really teeny, tiny arms. The exponents are the T-Rex arms of mathematics. Exponents have very short reach. They cannot reach very far. What is this squared touching? Only the 4. It has T-Rex arms. It is not long enough to reach that negative sign. We got it? The only way I can make the exponent have more reach is with parentheses, like in this first column. That squared now does reach the negative sign because I have put parentheses around it. I have allowed the exponent to reach everything in the parentheses. But otherwise, the exponent is only affecting the literal one thing it is touching. Okay, last column. -4 squared. We did this problem first, first column. So I'm going to copy this negative sign out here. And what was our answer to what's circled? Is 16. So that is the answer. But the common wrong way to do this one is to say, oh, negative times negative makes positive, and view this as being +4, and then we're going to square at the end. You see it? You've been trained. Hey, you see two negatives right next to each other, you cancel them and make them positive. But that negative on the inside is protected. It is not a negative. It has to be squared before you can really tell what it is. All right, so that one's -16, not +16. It's not that. Okay, so one more property of exponents before we go back and do the beast of a problem on the previous page. It says a to the 0 is 1. Any number raised to the 0 power is 1. Any number raised to the 0 power is 1. We're going to justify why this is true next class, but for right now, I actually do want you to just trust me that this is true. Any number to the 0 is 1. So here are the easiest problems in the packet for today. 4 to the 0 is 1. Really common to think an exponent of 0 would give you an answer of 0. It does not. I will justify that next class. But for right now, we're just trusting it is 1. How about this craziness to the 0? It is 1. If you see a problem like this in the homework or on a test, say thank you. Anything to the 0 is 1. Doesn't matter how ridiculous the thing in the parentheses is. How about -3r to the 0? 1. And then -3r to the 0. This is so much fun. All right, this one is not 1. Because again, the exponent is the T-Rex. And what is that exponent touching? Only the r, which means that -3 is hanging out, waiting for you to tell me what r to the 0 is. That's 1. And so how much is the whole thing? -3. Exponent only affects what it is exactly touching. All right. So let's go back one page to the problem we skipped. So here's the problem we are going to tackle. It is a whole big old fraction squared. I'm going to color code this here, times a whole other big old fraction cubed, right? Lots of x's, lots of y's. We've got divisions, multiplications, exponents, and then the whole two highlighted things are both being multiplied too. This is as hard as they get, and let me tell you, this is hard. But if we can do this one, then we have a very good handle on the properties of exponents that we talked about on the previous page. So the green one, we're going to separate these two and bring them together at the very end of this problem. So the green one has been separated out and typed out. We've got all this stuff. You can read this as a reference later. Basically, I'm going to say that, but we're just going to focus on the blue one for right now. And so let's take a look at that blue one. It is copied down over here. The first task is to reduce the fraction. And we're going to start by reducing the numbers in the fraction, not the exponents yet, just the numbers. 15 over 25, that is just an ordinary old fraction. What number goes into both? 5. How many times does 5 go into 15? 3. How many times does 5 go into 25? 5. And I'm going to try to practice what I preach when I say that oftentimes the biggest mistakes I see with students working these complicated problems about exponents is trying to do too many steps in one. I'm just going to do one step, and I'm going to copy everything else. Slightly annoying maybe to have to recopy this, but much, much less prone to error. Honestly, it doesn't take that long anyway. So we have reduced the number parts. Now we're going to reduce some of these variable parts. I'm going to focus on the y's first. I've got y to the 10th on top and y to the 3rd on the bottom. You've got your reference sheet with all the big numbers on it, right? Just have that handy. It's the one you ripped off before. Flip over to the back. I don't want to focus on the number page here. I want to go to the back. And on the back, the first 5 properties in this table are exactly the 5 properties we saw here together. And you need to figure out which of those 5 properties is the relevant one. So I'm going to circle the piece we're focusing on. It is right here. Focus on nothing else other than this, y to the 10th over y to the 3rd. 1 through 5. One of these properties looks like x to a power divided by x to a power. Which one is it? 1 through 5. Say the number. 1, 2, 3, 4, or 5. This is property 2. You see it? X to a power divided by x to a power. Am I right? Yep. X to a power divided by x to a power. And property 2 says we're supposed to subtract those powers. So I'm going to subtract the powers. I had 10. I had 3. I subtract them. I get 7. I get y to the 7. And this is the part where we have to make sure we know whether it's on top or bottom. Where will the y's end up when you subtract? Top, because there are more y's up there. So that's where they will be left over. So I am going to, big old fraction here, 3, 5, x to the 5th, x. And then I'm going to make this one change. Copy everything, but make one change. This becomes y to the 7, and it's on top. And the whole thing is still cubed. Okay, well that was so much fun. Let's see if we can do something similar for the x's here. I see x to the 5th divided by x. That is all I'm focusing on. Everything else is a distraction. Look at your page, looking for a property that says x to a power divided by x to a power. 1 through 5, say the number. This is again property 2. And again, what are we doing with the exponents? Subtracting them. There is an invisible exponent. You need to know what it is. What is it? That's an exponent of 1 down there. So I'm subtracting 5 minus 1. That's going to give me 4. So I'm going to copy everything else. 3 there, 5 there, y to the 7th there, whole thing cubed. And now we make the one small change. X to the 4th on top. That's it. 5 minus invisible 1. You put them where there were more x's. It's on top in this case. Okay, this fraction inside the parentheses is as simplified as it can be, which means we got to change our tactic now. We've gone as far as we can down this path. Now we're ready to expand our horizon, look beyond the parentheses. The whole thing is being cubed. We need to apply a property where the whole thing is being cubed. Fundamentally, this is a single fraction to the 3rd power, yes? A fraction happens to have some complicated things in it, but it is a fraction raised to a power. Look on your page, 1 through 5, those 5 properties. Only one of them is a fraction raised to a power. 1 through 5, which one is it? This is property 5. You see it? It is a fraction to a power. It's really important to be able to identify, to look at something complicated, but boil it down, you know, kind of like cross your eyes a little bit to make it kind of blurry so you don't get lost in details. It's just like fundamentally, what form does that have? There's only 5 choices. This is a fraction to a power. That's property 5. And so property 5 says you are supposed to pseudo distribute that power onto both the top and the bottom. So here's what we're going to do. I'm going to put both the top and the bottom in separate parentheses, just like it's written in property 5 on your page, right? X and the Y are both in parentheses, even though they weren't necessary. We're just going to put them there by habit. And then what's the power that both of them get? It's cubed. That is the 5th property. Give both top and bottom the right power. Okay, the bottom, 5 cubed, that's easy. If you don't happen to know it, we'll use the chart, but we're going to hold off on that. We'll do that at the end. But up on top, we've got more work to do. The top is more complicated. And so I'm looking at the top and again, trying to figure out fundamentally which of these 5 properties, again, look at your 5 properties. Which one is this? So here's what I see. I see things being multiplied, all in parentheses raised to a power. There is one property that has things in parentheses being multiplied with a power on the outside. 1 through 5, which one? That is 4. Now number 4 has only 2 things in the parentheses, x times y. This one has 3 things in the parentheses, but it doesn't matter. It's just an extension of that property. And so property 4, again, is a pseudo-distributive property, which means that everybody in the parentheses gets the right power. And so let's copy this 5 to the 3rd here. And then I'm going to, it feels excessive to do so many parentheses, but trust me, we want them. Everybody on the top gets its own set of parentheses, exactly like in property 4, where the x and the y both got their own set of parentheses. And now what power do each of these 3 things get? 3. They all get cubed. So if I see that property, that was number 4. Okay, so let's do one more step here. Big fraction. Okay, 3 to the 3rd. You might happen to know that one, but even if you don't, look on the back of this thing with all the properties on it. The first column is number, the second column is perfect squares, the third column is cubes. That's what we have here. So can you see 3 cubed in that list? That's 27. I'm going to skip to the bottom. The bottom is 5 cubed. Find it in the list. Go to the 5 in the first column. Read off 5 cubed from the cubes column. What is it? 125. That goes right down in the bottom. Again, we got to make sure that we can read off of the chart because I'm going to take your calculator away on quest 3. It's the only time I'll do it. Okay, so we dealt with the number parts. Now we have the variable parts. X to the 4th to the 3rd. Flip this thing over. Looking at our 5 properties again, I'm looking for x to a power in parentheses raised to another power. 1 through 5, which one? This is 3. We see it? X to the m, the whole thing raised to the n. What do we do with those powers? We multiply them. And so we are going to multiply the powers. So in the first case, x to the 4th to the 3rd, we multiply and get 12. And then we look at y to the 7th to the 3rd. It's the same exact property, number 3. It says you multiply those powers, gives me a y to the 21. You can see all the opportunities to make mistakes in these problems. You could reasonably say, oh, 4 and 3, I add them, I get 7. It's perfectly reasonable. It's not right. You got to make sure you are correctly applying the property. Find the right property and apply it. Okay, so we have done everything we can with this one side. There's no parentheses anymore. It is as simplified as possible. We can go no further with this piece. But in the very beginning of the problem, there was another piece. It's highlighted up here in green. We did blue as far as we can. Green is done. We didn't read it, but it's the first column. We're just going to grab the final simplified version of green at the bottom. But you do these two pieces as far as you can separately, and then we're going to bring them together and do the final pieces of this problem. So I'm going to highlight again. So ours was the blue one, I think, right? We did blue, and green is typed up on the left-hand side. I think I've got that right. Green and blue. Okay, so the green thing here does not look familiar to us, but if you just read and follow the same process we did, you will end up with that. Our red thing is copied right there, 27x12y21 over 125. And now multiplying fractions, do we need a lowest common denominator? No, we just multiply straight across. That's how we multiply. And so that's written out over here. No work has been done. It's just been copied into a single fraction, literally 81, x to the 6, 27, x to the 12, right? Just copied in order. All right. And now that we have a single fraction, we're ready to finally smush these two things together and simplify in our final step. Okay, 81 times 27 is a calculator thing. You just type it in, you get 2187 apparently. Downstairs, I've got 49 and 125, and that multiplies to 6. We're saying true things here. 7s, 5s, yeah, we're saying true things. 6125 is what you get when you multiply those. Nothing to it, just type it on the calculator. Okay, but now we're going to focus on the more interesting pieces here. So we have got up here, x to the 6th, x to the 12th. In my mind, they are right next to each other. Multiplication, I can just shuffle things around in any order. Look at the 5 properties. This is one of them. X to a power times x to a power, 1 through 5. Which one is this? This is the first property. We see it? And what do we do according to that first property with those powers? Add them up. So it becomes x to the 18. And you put it wherever they were. They were both on top. Clearly, that's where the 18x's will end up. And that is right there. Okay? And then the last piece, blue. Here we go. Y to the 21, y to the 10. There's lots of distractors around these things, but that's what I'm seeing in my mind. Just the y's. 1 through 5. It's one of these properties. We've seen it before. Which property is it? This is the second property. What do we do with the exponents? We subtract them. And we subtract them, we get y to the 11. Where do you put the y to the 11? Top, because that's where there are more. Y to the 11 up there. And that's the simplified final version of this problem. Technically, we should have to make sure that 2187 over 6125 is reduced. It is, but that's the only last piece to this, is that you might have to reduce some numbers at the end. Whew. That's a doozy. This is as hard as they get. But I want us to be able to do the problems that are as hard as they get. There's 5 properties of exponents. It's really easy to pick the wrong one. It's really easy to misapply the right one. It's really easy to do the right property, but in the wrong order. There are so many ways to get these ones wrong. I'm hoping, I know this took a while here. I'm hoping that the process that I laid out gives you a recipe, something that you can follow. It's really important not to just like think, oh, I think it's this third property. It kind of has the right pieces. That there's no haziness here. Like you have to know firmly, like this is the form that I'm in, and only one of these 5 properties is going to be the one I can apply first or next. Okay. All right. So we did that page already. We're skipping to the activities here. So the first question here is the only like diagram one. Everything else is exponents. Which theorem do you think we're going to use, even without reading? The Parian Theorem. Can I ask you to skip that one? I honestly think it's going to be no problem for you, and jump right down to the box right here. We're going to get as far as we can with these problems very carefully.